How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at phases and intermolecular attractive forces, or IMAFs for short. Our objectives will be to identify the physical differences between liquids and solids, as well as compare the different types of attractive forces, determine when they would be present, and predict their physical properties based on the IMAFs present. All right, so solid, liquid, gas, let's talk about them. Solids, think about ice. Ice is solid water. If we did a particle diagram, you can see that the particles are arranged in this nice, neat, repeating pattern. So the solids have a definite shape, they have a definite volume, they vibrate in place, and they're incompressible, meaning if you push down on them, there's no empty space for them to get compressed into. Liquids, similar but different, right? So liquid particle diagram might look like all the little particles are able to flow past each other, and they're taking the shape of their container. They have a definite volume. They flow past each other, and they're incompressible. Whereas gases, think about steam coming off your teapot. All those particles are really spread out. They take the shape of their container. They take the volume of their container as well. They flow past each other, and they're compressible because there's all that empty space between the gas particles. All right, so if we're talking about intermolecular attractive forces, we're talking about how attracted those particles are to the other particles. For solids, that's where they're the strongest. When you heat them up and you melt them and you get the liquid phase, they become weakened. They're like the middle, the moderate intermolecular attractive forces. Whereas gases, they're the weakest out of the three phases. So they have really weak intermolecular attractive forces. In fact, most of the time we say there aren't any. There's so little that we can ignore them and say there's zero. All right. Important vocab to distinguish between. We have intermolecular and intramolecular forces. So intermolecular forces are between different molecules, right? If you think of inner states, they go in between different states. Whereas intramolecular, they're forces that are within the molecule. So inter is like how strong is molecule A attracted to molecule B, whereas intra is within that molecule. How strongly is atom A bonded to atom B in that molecule? So using water as an example, intermolecular forces, how strong is that attraction between these two different water molecules? Whereas intramolecular forces is how strongly is the hydrogen bonded to that oxygen in the single molecule of water. So intermolecular forces are weaker than intramolecular forces, which means as you add energy to a substance, it's more likely to separate the molecules from one another than it is to break apart the molecules. Right? So I add some energy, I'm separating those two water molecules, as opposed to, hey, I added energy and I broke that molecule apart. That's not what's going to happen. All right, so I got this little what do you call this concept map, this little graphic organizer for intermolecular attractive forces. We know that they are attractive forces between molecules. All right, so let's take a look at IMAFs and their properties. So we know IMAFs hold molecules together. In order to change phases from solid to liquid to gas, these attractions need to be overcome. So the stronger the intermolecular attractive forces are, the higher the temperature will need to be to make these transitions. So if you have really weak attractive forces, it might be pretty easy to melt that solid to liquid, but if they're really strong, you're going to need more energy. The temperature is going to have to be higher. So here's some physical properties. Which one of these has the strongest intermolecular attractive forces? All right, we got substances and we got boiling points. So we know that if the intermolecular attractive force strength goes up, well, then it should be harder to vaporize them. So the boiling point should also go up. So which one of these has the strongest? Looks like xenon would. And if we take a look, oh yeah, that's just the right answer. There you go. All right, so what causes these intermolecular attractive forces? It comes down to charges. So we know that opposite charges are attracted to each other. So if you think about ionic bonding, we have this positive cation attracted to this negative anion, and that opposite charges attracting is what making that ionic bond. It's similar with intermolecular attractive forces, but they're much weaker than ionic bonds. And the reason for that is in ionic bonds, we have these full positive and full negative charges, whereas when we're talking about molecules, we have just partial negative and partial positive. So the charge difference between them is much smaller. So charges and covalent compounds. Let's start with the simplest example of a helium atom. So we know that a helium atom has 2 protons, has 2 neutrons, and has 2 electrons. So electronically, the whole thing's neutral. So you may be asking, hey, where are there charges coming from in this helium molecule if the whole thing's neutral? All right, well, it comes down to the electrons and the fact that they move. They're not in one place on the atom. They're orbiting around the atom, and that's going to impact the charge. So we know the electrons are orbiting around the nucleus. At any given moment, there may be more electrons on one side of the atom than the other. Right? So, hey, at this very moment, those electrons are on the left side of that molecule. That side's going to become more negatively charged, and then the opposite side is going to become more positively charged. The whole thing is neutral, but in this instant, those 2 electrons are on one side of the molecule, making that side negative, and the other side is going to be more positive. So if I color-coded it, it would look like this. We have a really negative end and a positive end on that molecule, just because the electrons happen to be on one end momentarily. So these momentary dipoles can cause nearby molecules to also become polarized. So if I had this other helium molecule neutral, but hey, now it's close to this, this molecule A that has this momentary dipole, the positive region on molecule A is going to attract the electrons on molecule B. That's going to cause the electrons to shift and cause B to become polarized as well. So just one being nearby, happen to be polarized, can polarize another nearby molecule. Now these molecules will be attracted to each other, even if it is only momentarily. All right, so dispersion forces. The type of intermolecular attractive force that we just described is called a dispersion force. So dispersion forces are instantaneous dipole on one molecule inducing an instantaneous dipole on an adjacent atom, causing the atoms to be attracted to each other. Right, so I have this, hey, for a moment, A has this instantaneous dipole, and it's going to induce a dipole in another molecule. So for that moment, they're going to be attracted to each other. These forces are also known as London dispersion forces or induced dipole interactions. So watch for that. So graphic organizer, dispersion forces, instantaneous dipole inducing another instantaneous dipole. So dispersion forces continued. They're more significant when the molecules are closer together. So as you see on the left, A and B are pretty close together, and on the right, A and B are pretty far apart, and you see B didn't polarize as much as the one on the left did. So think about magnets. The closer they are to each other, the stronger the pull is. So the closer that the molecules are to each other, the stronger these dispersion forces are going to be. That means it's going to be strongest in the solid phase. It's going to be stronger in the solid phase than in the liquid or the gas phase. Polarizability. It's basically just how easily is the charge distribution distorted? How easily is that molecule polarized? So if it's easy to distort, we call that very polarizable, and that means you will have stronger dispersion forces. So you can see on the left, hey, that thing polarized really easily, became very polarized just like A. But on the right, hey, this one's more difficult to distort. It's not going to polarize a whole lot. It's going to have a weaker dispersion force. Now the pattern in general for polarizability is the larger the molecule, the more polarizable it is, and the stronger the dispersion forces are. So large molecules means that they have more electrons. And if there's more electrons to work with, they can be more polarizable. So if I'm taking a look on the left, hey, small molecule, we only got 2 electrons versus 1 on the right. We got a whole handful. At any moment, hey, those 2 electrons are on the left and positive charge is going to be on the right. But if I have more electrons to work with, I can get a bigger charge difference. So which substance has the strongest dispersion forces? Here's some examples and their molecular weights. Well, we know that as molecular weight goes up, so does the dispersion forces. So if we want the strongest one, we're looking for the one with the greatest atomic weight. All right, well, it looks like it's going to be xenon. And now if I refer back to what their boiling points are, hey, wouldn't you know it? That's what I said. The strongest dispersion forces is the one that has the highest boiling point. Nice. All right, which substance has the weakest dispersion forces? Again, if I want the weakest, I am looking for the lightest one, the least polarizable, the smallest one. And then here they give me the molecular weights. It looks like the smallest one is F2. Let's see what their boiling points are. Hey, wouldn't you know it? Out of all those options, F2 is the one with the lowest boiling point. All right, dipole-dipole interactions, the next type of IMAF. So we can have covalently bonded atoms, right? And they share electrons, but this sharing is not always fair or equal. Sometimes we have polar bonds where electrons spend more time around one atom than the other. So you can see in the H2 molecule up top, the electron is shared evenly between those two hydrogens, which means the charge is going to be evenly distributed. But in the HCl, chlorine is more electronegative, so it's going to hog that electron. The electron is going to spend more time around the chlorine than around the hydrogen. So that means the chlorine is going to become slightly more negative because the electron's hanging out there more, and the hydrogen is going to become slightly positive. So those are the symbols for partial negative and partial positive. If we take a look and like color-coded charge distribution, H2, perfectly neutral overall. Whereas HCl, we're going to have a slightly negative end and a slightly positive end. Chlorine being more electronegative, it's going to be the negative end. These are what cause the dipole-dipole interactions. So dipole-dipole interactions, it's the presence of a permanent dipole in a polar molecule, which causes attraction between positive region of one molecule with the negative region of another. So let's go back to our graphic organizer. Boom. Dipole-dipole, permanent dipoles and polar molecules attracted to each other. And now collectively, these two types of forces are sometimes referred to as van der Waals forces. So if you ever see van der Waals forces, they're talking about both dispersion and dipole-dipole forces. All right, so dipole-dipole interactions. As the polarity of a molecule increases, so does the strength of the IMAF. So if I take a look at these two different molecules, they have similar molecular weights, so the dispersion forces we're going to say are going to be really similar. So any difference in their physical properties is going to be due to the dipole-dipole interactions. And if we take a look, all right, I got this pretty neutral atom. There's no dipole there. But then on the other molecule on the right, you see the nitrogen's going to have the negative charge on that end. So now I have this permanent dipole. I have a permanent negatively charged end and a permanent positively charged end. So what's going to happen when these two molecules interact? Well, the ones on the left don't really have any difference in charge, so there's not going to be any real dipole-dipole interaction there. Whereas the one on the right, hey, the negative end of this molecule is going to be attracted to the positive end of the other. We're going to get that attraction because of the difference in charge. And if we take a look at the boiling points, you can see the ones with the dipole-dipole interaction are significantly larger than the ones that don't have it. Right? So again, these attractions are also more significant the closer together those molecules are. So just like magnets, like I was saying before, the closer they are, the stronger that attraction is. So the attraction is going to be the strongest in the solid phase when they're really close together. Hydrogen bonding. When hydrogen bonds with nitrogen, oxygen, or fluorine, it creates a really polar bond, which makes the attraction significantly stronger than a typical dipole-dipole force. So if I take a look at HCl versus HF, you can even see the difference in charge is significantly greater. It's more than twice as great in HF than it is in HCl because fluorine really hogs those electrons. So we get a significantly more negative charge there. And you can see as a result, the boiling points are drastically different. So why is that? What's going on? What's special about nitrogen, oxygen, or fluorine? So we know that hydrogen has no shielding electrons. It's basically just a proton and an electron. So when hydrogen bonds with nitrogen, oxygen, or fluorine, those elements really hog those electrons because they're really electronegative. So that means hydrogen spends a lot of time without its only electron. So essentially, there's just a proton sticking off of a fluorine. This makes it very, relatively speaking, positive, allowing for a strong intermolecular attraction. So fluorine almost entirely hogs that electron, so it becomes very negative. And then hydrogen's just this proton, this positive charge sticking out over there. So these interactions between these molecules are going to be really strong. So graphic organizer, hydrogen bonding. When hydrogen bonds with nitrogen, oxygen, fluorine, it creates a really polar bond, which makes the right. Okay. Ion dipole forces. They exist between an ion and a polar molecule. So the positive cations are attracted to the negative pole of a polar molecule, and the negative anions are attracted to the positive pole. So often we have water as a solvent, right? So this is what's responsible for ionic compounds dissolving in water or other polar solvents. So for example, NaCl in water. What happens is, well, I know the oxygen end of the water molecule is slightly negative, so it's going to be attracted to the positive cation, sodium. And the positive ends of the water by the hydrogen are going to be attracted to the negative chlorines. So the water molecules start to surround these ions, and they start interacting with the ions and tear apart the ions from the ionic solid, and that's what's happening when things dissolve. So that's our last attractive force we're going to talk about. But let's talk about comparing intermolecular attractive forces and their strength. Usually dispersion forces are the most responsible attractive force in a molecule and are found in all substances. So all substances will have dispersion forces. And you can see the relative strengths of these things and how they compare. So you see dispersion forces can be pretty good. Dipole are, on the lower end. Hydrogen bonding, significantly stronger than dipole. And then ion dipole are really, really powerful. But the thing about attractive forces is they're additive. And what that means is, like, if everything has dispersion forces. But if you're comparing a molecule that only has dispersion forces to a molecule that's similar, has dispersion forces, but also dipole, well, that dipole adds to the attractive force. It's going to be stronger, right? So if I'm taking a look at these two molecules, this only has dispersion, but this has dispersion and dipole. So its attractive forces are stronger. The boiling points are higher. And then again, continuing on, if you have dipole, that's not going to be as strong as if you have dipole and hydrogen bonding, right? So for example, HCl versus HF, they both have dipole, but fluorine bonded to hydrogen causes hydrogen bonding, and the boiling point jumps up. That attractive force adds on to the dipole. And then again, hydrogen bonding. If you have a molecule with one hydrogen bond versus two hydrogen bonds, well, let's see. There's where's my pen at? There's one chance for hydrogen bonding between this molecule, but here there's two. Now the attractive force adds together. So of course, two hydrogen bonding makes it a stronger attractive force than just one. And if you take a look, the boiling points are different. The one that has more hydrogen bonding has a higher boiling point. So how do you know which ones you got? What attractive forces are present? Dispersion forces attract in every molecule. Dipole only occurs if it's in a polar molecule. Hydrogen bonding occurs only in a polar molecule that has hydrogen bonded to nitrogen, oxygen, or fluorine. And then ion dipole is, ionic solids with a polar liquid. So there's like kind of this little flow chart that I find helpful. First question is it a polar molecule? And then if no, then you only have dispersion forces. If so, you got to then ask, hey, is there hydrogen bonded to NO or F? If not, then it's just dipole and dispersion. And if it's yes, then it's got those three. All right, summarize. Can you identify the physical difference between liquids and solids? And then compare the different types of attractive forces, determine when they would be present, and predict their physical properties based on the IMF present. I hope you found that helpful. See you in class. Okay, bye.